memory. Whether it be DDR, GDDR, NAND flash, or SRAM, they've all got one thing in common. They're one of the more expensive parts of a modern computer when looking at price and capacity, yet without it your PC couldn't function as it doesn't have anywhere to keep its data. This is true for almost all computationally focused integrated circuits, and when looking at things from a macroscopic view, you've got several different types of memory and storage all working together to transfer your data between the components of your machine. The focus on this video, however, is going to be on VRAM, specifically how it works and how much of it you need in 2021. It might surprise you as to how much you actually need for gaming, as it's probably not as much as you think. Like previously mentioned, we're going to first take a look at exactly what VRAM is, and how it functions as a cog in the overall machine. To achieve this, we first need to differentiate between storage and memory, specifically in the roles they play. Storage refers to circuitry or magnetic poles that store bits for long periods of time. This is often referred to as secondary storage and includes things such as NAND flash-based NVMe drives that have become so popular in the recent years. Magnetic hard drives and even the new Optane, although there is an aspect to it that makes it behave more like memory while serving as secondary storage. It's kind of weird, but segues nicely into how memory behaves as opposed to storage. Memory refers to temporary buffers in your system used to store data for processing. Examples of memory include your DDR DIMMs, the cache in your CPU, and also the VRAM on your graphics card. The vital difference with memory is the temporary nature of the data. When power is lost or cycled, the data being stored is lost, meaning it must be refilled in order to serve any real function. Storage retains its data through the power loss, which is where Optane's behavior straddles the line between memory and storage. This won't be a dedicated video on Optane, as I have a separate video coming on the interesting quirks and uses for Intel's fledgling technology, but what I will say is that it functions with speeds faster than traditional NAND flash while retaining data through power cycles. This means that your CPU can work directly on storage instead of working from storage. You can find Optane DIMMs online, and it's an awesome technology that is ripe for engine nerds like you and I. But back into VRAM and how this specific technology works. VRAM, like your system's SDRAM, is based on capacitor memory, which uses voltage to store and interpret data. SRAM, like what's found in your CPU's cache, uses transistors to store values, switching them between an on and off state. SDRAM works as a massive array of capacitors hooked up to transistors, which functions as gates that allow charge into and out of the individual capacitors. You can make a very simple DRAM cell on your own with a single NPN transistor, a single capacitor, and a resistor. When you shrink these cells down and hook them up to bit lines, you then can read and write to them in blocks, meaning you can store more complex sets of data or instructions. The actual memory cells don't necessarily need to know that they're storing data, but they do need to be able to report its value and obtain a new one. On your graphics card, you'll see VRAM chips surrounding the actual substrate or interposer, but there is an exception, that being HBM. HBM, including its newer and more efficient 2.0 and 2E flavors, are actually stacked either on the die itself or directly next to it, giving it a more integrated and compact look, while also making cooling easier since it sits under the same cold plate as the die itself. GDDR chips in opposition sit on the PCB, and by and large take up more area on the board than HBM alternatives. The chips come in different shapes and sizes depending on which generation they're from. VRAM, when written as GDDR6 or GDDR6X, both refer to a type of memory optimized for smaller and tile-based pieces of data, meaning that less data can be accessed but can be pulled into the cores more quickly. This can be countered though by increasing the bus width of your memory controller, usually mentioned in terms of the bit width of the bus, but doesn't actually represent a full bandwidth number. The other thing that complicates this is GDDR6X, which actually transmits 4 bits per clock cycle per line, as opposed to the standard 2 found on straight GDDR6. The issue with GDDR6X though is signal integrity, which explains why the chips are so tightly packed around the Ampere dies this generation, but also means that massive 512-bit buses are unlikely to show up on this memory type in the future. In essence, your VRAM acts like a place to store files and data locally, increasing the overall bandwidth to the processing cores, but also and more importantly, decreasing access times. Without the onboard VRAM chips, your GPU would have to access your main system's memory, which requires a communication jump through PCIe, and ultimately actually has a smaller bus to work with depending on the configuration of your card. Even though accessing main memory may seem like it would be more beneficial, as the size is usually much greater and would also avoid expensive file transfers, it actually is much more costly in terms of retrieval latencies simply due to the proximity of the circuitry. When you look at a motherboard, there's a general layout that most boards built over the past 20 or so years follow, with your PCIe slots being located under the CPU socket with your RAM next to it. Looking at things from a circuitry perspective, that means that any memory transfer has to first be initialized by the GPU, sent to the CPU, interpreted by the CPU, pulled from RAM, and then sent back to the GPU from the CPU, where the GPU can then do whatever it needs to do. If you're curious and want to see this transfer taking place, all you need to do is go into a game that allows you to see your VRAM usage, or use MSI Afterburner. In this case, I'll be using Warzone because it's a newer DirectX title, but even older games such as GTA 5 would work as well. To get the VRAM buffer filled, just turn up settings until your memory is full, then turn down settings one by one to see how it affects your actual memory usage. I found those through some testing that texture quality usually has the biggest impact on this, but if your card is capable of 1080p gaming at max settings, setting everything to ultra will do the trick as well. Let's hop in game and take a look at the MSI Afterburner overlay to see what's going on under the hood. While you're sitting in the menu, usage stays relatively low, usually under 2 GB for me. However, when you begin loading into the game, your VRAM allocation will start increasing, which is visible through just watching the reported figures. Memory is a dynamic thing, meaning it can be freed or mallocked on the fly, and this has the upside of allowing for the programmer to use it as a scratch pad that can be modified. From a technical sense, this can also create things called memory leaks, where a program isn't deallocating memory, causing its usage to balloon uncontrollably. Minecraft Java Edition is a good game to look at if you're interested in memory usage, as the garbage collection of Java just leaves tons of data in your system's memory pools. It's an interesting concept that most programmers have to deal with at some point in their career, but if you're smart about how you're writing your software, leaks can be avoided. Moving into tests, let's run a few games on my graphics card and take a look at how memory usage scales with resolution. For these tests, I'll be using my water-cooled Titan X Pascal, a 16nm base card with 12GB of GDDR5X. To keep memory bandwidth high, I overclocked the memory modules to hit 11GB per second of throughput on the chips, and 528GB per second on the GPU itself. The wide 384-bit memory on this card also allows for the card to transfer larger chunks of data per clock cycle, meaning bandwidth is increased and is much more power hungry than a reasonable 256-bit interface. This card, while definitely showing its age, has more than enough VRAM to power through any title, making it a contender to test memory usage as we aren't in danger of running out. Let's dive into the games though and see how much VRAM you need in 2021. Starting off with Cyberpunk, and I ran through 3 resolutions to see how VRAM usage scaled with the increase in pixels. Starting with 1080p, and here we see the card allocating around 5.5 gigs of memory to the game. Textures and other heavy compute settings are turned on here, with sprites and volumetrics being set to their respective low values. This helps us maximize the memory footprint of the game, while allowing for smooth performance at all resolutions tested. Moving up to 1440p, and the usage jumped up by about 300 megabytes. But 4K is where we saw the most usage, with over 6.5 gigs of memory being used. It's kind of incredible to think, but a GTX 1060 could run this game seemingly comfortably at 1080p. And the fact that the game will most likely run out of memory on a 4GB card is kind of unfortunate, but is the ultimate cost of progress. Red Dead Redemption 2 at 1080p is actually a relatively well optimized game, and with a mix of high, medium, and low settings, VRAM usage settled in at around the 4.5 gig mark. Jumping up to 1440p and the allocation jumped up to over 5GB, and the game looked a bit better, but overall it's impressive how roughly doubling the resolution only increased usage by about 700 megabytes. 4K caused memory usage to jump up to over 6.5 GB, which while expected and leaves a lot of breathing room for this particular card, shows that this game has the potential to max out 8GB cards at higher settings and resolutions. Battlefield 5, a game built on DICE's Frostbite engine, was actually relatively well optimized, with 1080p max settings using only around 5 to 5.5 gigs of VRAM. Raising the resolution to 1440p didn't affect usage that much, with only a slight increase in the amount of used memory, hanging out around 5.7 gigabytes. 4K though was an entirely different story, with usage jumping up by almost a gigabyte. Even though usage hung around 6.5 gigabytes, lowering settings would help to bring usage down, and at low settings the game could comfortably fit inside a 4 gig buffer. These settings though seem to take up a nice chunk of VRAM, so if you're struggling to run this particular game on a 2 gig card, that's probably why your performance is poor. Up next is Call of Duty Warzone. And one thing I noticed while testing was the game filling up the entire frame buffer on the card no matter the resolution. Digital Foundry mentioned this once, that this game uses VRAM as a texture cache, and fills it based on availability rather than what's required to run the game. To check this, I ran the game at 1440p maxed out on both my Titan X and my GTX 1080. And sure enough, the game was using 12 gigs of VRAM on the Titan and 8 gigs on the 1080. The game is just filling up the entire VRAM buffer, irrespective of whether or not the game actually needs the memory. This makes benchmarking VRAM usage difficult, as it uses all of it, and doesn't actually give us a good idea as to how much you would need. It's because of this, and from experience, that Warzone only really needs 4 gigs of VRAM to run smoothly at 1080p, and 6 gigs if you're looking to go beyond. Overwatch, a rather popular esport title, used only around 4.5 gigabytes of VRAM at 4K max settings. Because usage was so low, I expected the game to fit comfortably into a 2 gig frame buffer at 1080p and below. Unfortunately, the game used just over 3 gigs of memory at 1080p, so if you're eyeing up a 2 gig card to play esports titles on, while it might be playable, it'll also introduce some stuttering in game due to memory swapping, so 3 gigs is the lowest I would comfortably recommend for this game, albeit the configuration is relatively rare. Overall, VRAM usage was actually relatively consistent between all our games, with Warzone being the outlier. If you want a guide as to how much VRAM you'll need in 2021, then based on the results of the games tested, it appears as if 4 gigs is enough for 1080p gaming, with some settings turned down. 6 gigabytes is good enough for 1440p gaming at lower settings, with 8 gigs and above coming in for 4K at lower high settings. Optimally, you would have 12 gigs of memory on every card available, but due to economics and the bus widths available, cards today ship with anywhere between 2 and 24 gigs of VRAM. And not to mention some cards, specifically the RTX 3060, actually rock more RAM than any card in the Ampere lineup up until the 3080 Ti. This confuses customers as a more expensive RTX 3080 has less onboard memory than a cheaper, much less powerful card, but for me personally, I see this as a massive win for the consumer. Even though it is kind of confusing, the RTX 3060 at the end of the day doesn't really need all that memory for gaming. But this makes the card an attractive alternative for budget workstation builders. What I'm trying to say is that while having more VRAM is nice and is definitely welcome, at the end of the day, if your workloads aren't taking advantage of it, then it's kind of going to waste. It's because of this I'd recommend a 4 or 6 gigabyte card for your budget 1080p gaming system, with 6 gigabytes allowing for higher resolution textures and less visible pop-in. 8 gigabytes is what you'll find on most mid-range cards nowadays, and for 1440p gaming that's more than enough. 8 gigabytes is also enough to edit 4K footage, which speaking from experience wasn't actually all that bad of an experience. If you're eyeing a card with higher capacities, say the RTX 3080 with its 10GB buffer, just know that for gaming you won't see tons of improvements by just increasing your memory capacity. However, going back to the lower end of things, there are literally millions of GPUs paired up with 2 gigs of memory out in the wild, meaning you're more than likely going to come across one in your search for a budget card. Even though it might be tempting, it's ultimately not worth buying anything with 2 gigs of memory on it in 2021 for anything remotely taxing on compute. If you plan on doing other things on your system as well, such as CAD work or PCB design, that's also where you'll benefit more from more VRAM. It's tough though because there isn't a one-size-fits-all solution to this issue of memory capacity, because everyone uses their machines differently. What I need to accelerate my specific workloads will be different from what you need to get the most out of your own workloads, and that variability is what makes making recommendations so difficult. However, given you follow the rough parameters I laid out in this video, and do some of the math, you should get an awesome experience from your gaming PC, where VRAM is plentiful for what you need.